Let's see an example of the use of the integrated rate laws for the first order decomposition of hydrogen peroxide. The rate constant for this reaction is provided, and the initial concentration is given to be 0.75 molar. We're asked to determine the concentration of peroxide after 3 hours, and we're also asked the time it would take for the concentration to drop to 0.10 molar. We're going to use the first order integrated rate law because the reaction is first order. In part A, we're asked to calculate the hydrogen peroxide concentration 3 hours into the reaction. We first have to decide which form of the first order integrated rate law to use. Because we want to know concentration, we're going to use the form that solves for concentration. So the peroxide concentration at 3 hours is equal to its initial concentration times E raised to negative kT. Substituting the given values, concentration is 0.75 in the beginning of the reaction. Rate constant is 1.8 times 10 to negative 5 per second, and time is equal to 10,800 seconds. We did a time conversion here from hours to seconds because the time unit that you use must match the units of time in the rate constant. We converted 3 hours to seconds. Calculating gives the peroxide concentration as 0.62 moles per liter 3 hours into the reaction. In part B, we're asked the time that it takes for the peroxide concentration to drop to 0.10 molar. Because we are solving for time, we're going to use this form of the integrated rate law. Substituting the given values of concentration at time equals T divided by initial concentration and the rate constant, we solve time as 1.12 times 10 to the 5th seconds. If time is asked in a different unit, of course you need to do a conversion from seconds to whatever unit desired. In this example, we are given the isomerization reaction of cyclopropane to propene. The rate constant is given 9.2 per second. The initial concentration is 6 molar, and we're asked to calculate the concentration after 1 second. In order to solve this question, we have to know the order of the reaction so that we pick the correct integrated rate law. But within the question, the order is not provided. So which integrated rate law are we going to use? The order of the reaction is revealed from the units of the rate constant. The unit per second reveals the order of the reaction to be first order. Therefore, we are going to use the first order integrated rate law. So if the order of the reaction is not given with a question, but the rate constant is provided, you can use the units of the rate constant to find the order of the reaction. Then you can use the correct integrated rate law. Remember, the units of K is equal to molarity raised to power 1 minus the order times per second. Therefore, using this relationship, you can figure out the order of the reaction starting from the units of K. Because we were given the initial concentration and asked the concentration at 1 second into the reaction, we're going to use this form of the integrated rate law. We substitute initial concentration 6 molar, rate constant is 9.2 per second, and the time is 1 second, which calculates the concentration at 1 second to be 6.06 times 10 to negative 4 molar. Now in this question, you are going to apply the first order integrated rate law to the radioactive decay of the tungsten 188 isotope. Here's another application of the integrated rate law. By measuring concentration at certain times in the reaction, you can apply the integrated rate law to solve for the rate constant.